of those. So we're going to do this in 3 speakers. We'll do them in sequence. I'll introduce them each in turn, not all together now. And if I can contain their enthusiasm, we'll have some time for questions and answers at the end. Our first afternoon speaker will talk about the NASA SwampWorks and the Granular Mechanics and Regolith Operations, GMRO, lab within it. NASA's a cool place to work, but it is a government bureaucracy, just like all others. The SwampWorks is a segregated activity created by our speaker, where the principles of innovation rule, with less of the constraining rules of any large organizations, and some of you can probably feel the pain of that. And the GMRO lab is essential because the first development of habitat on the moon must use the existing materials that are there. You will hear how the concept for a rapid lunar proving ground will require the combined expertise in regolith, robotics, and space resources. Now, Rob is a senior technologist and principal investigator in the Exploration Research and Technology Programs Directorate at NASA's Kennedy Space Center in Florida. He is the co-founder of NASA SwampWorks. He is the former chairman of the ASCE Committee for Regolith Operations, Mobility and Robotics, and the ASCE Aerospace Division Executive Committee. He also created the Open Solar System Foundation, a platform for all to participate in model-based open source design. I met Rob 7 years ago at an ASCE convention when we rolled out Future World Vision, and he and I discovered that we thought alike about how the profession needed to transform. I'm extremely happy to have Rob with us, especially after my moment of anxiety 6 weeks ago when I heard the news of the death of Robert Mueller. But then I realized Rob always investigated space interference, not Russian interference. So with that, Rob, over to you.
Thank you, Jerry. So first thing I'd like to point out to you is that the moon is not flat. If you look at this picture, in the Apollo 11 mission, which was the first moon landing in 1969, it was very flat. And it was flat for a reason, is to try to increase the odds of a safe landing. And so they picked the mare. Mare is a Latin word for sea of lava. So it was literally a sea of lava, and it was very nice and flat. But now things have evolved. In the later missions, in Apollo 16, 17, they went to areas like this, which we call the highlands. So a little bit of trivia for you: when you look up at the moon at night, you see dark areas and you see light areas. The dark areas are basaltic, they're mare, so they're flat, very even, and they're mainly on the near side. The far side doesn't have very many mare. But then more importantly, the light areas you see are made of a mineral called anorthosite, and it is the highlands. We call that the highlands, and the moon is predominantly the highlands. And the highlands are not flat. And we are going back in the Artemis program. NASA is going back to the south pole of the moon, not to the equatorial regions, which is where Apollo went. And so we're dealing with a different geology, a different topography, and different orbital mechanics to get there. So this is not going back to the moon as we did. And if you did go to the moon and visited an area the size of the mall in DC, you know that's not exploring the world. That's not exploring the Earth. So how can you say you've been to the moon? You have. So that's the whole thing, is that Artemis is different from Apollo, and we're going to the South Pole. And the reason we're going to the South Pole is because of resources, water ice. Impacted into the moon, the LCROSS mission, and the ejecta was measured by a mass spectrometer on orbit, and it did confirm there was 5.5% water in the regolith at the South Pole. Not everywhere, just in the permanently shadowed craters or shadowed regions. For 4.5 billion years, there has been no thermal change, so it's at about 40 Kelvin. And it's a phenomenon where it's called a cold trap, where the water ice accumulates in the permanently shadowed regions. And there's various mechanisms for how it accumulates there, but basically it's a thermodynamical principle where water wants to go to its most thermodynamically stable state, so it hops into the cold areas and then accumulates there over billions of years. So we do have a lot of water ice on the moon, but it's in the cold traps, in the permanent shadows, mainly at the South Pole and the North Pole. South Pole has more. NASA chose to go to the South Pole of the moon. So that's just a little bit of background on the Artemis program. Now, I'm here to talk more about innovation, and we do have, back to Artemis, is the moon base. Moon base was announced as a real program, and it has a significant budget behind it. So this is the first time NASA has become really serious about building a moon base, which should be very interesting to this community because it involves architecture and construction. And the thing we need to do first is some master planning of a moon base, and that is not happening. So this, it's not happening with a rigor that this community is used to. So we need to start that conversation of how to master plan a moon base. SwampWorks is an innovation environment that I co-founded with a few other people at a grassroots level in 2012 is when we officially started. So we've been around since then. And the main premise of SwampWorks is that after about 15 years into my career, I had been working space shuttle program, International Space Station. I worked on X-33, I worked on orbital spaceplane, a variety of NASA programs, the big ones. And I realized there wasn't a whole lot of innovation happening. It was actually, it was not think outside the box, it was don't you dare think outside the box. That's the culture I was living in the space shuttle program and the ISS program. And the reason why is because these are operational programs and they don't want risk. Zero risk tolerance. So don't you dare think outside the box. Follow instructions. That didn't sit well with me. That's not the kind of person I am. And I didn't think we could make much progress in space if we kept working that way. So we formed the SwampWorks, and it's basically based on two things. I realized that people will not innovate unless they're given permission to innovate. It sounds silly, but human nature is such that you will not risk your career on innovation unless your management tells you, we want you to innovate. So that was step number one, is create an environment where we tell everybody working in that environment, not only are you allowed to innovate, we expect you to innovate. And that's key step number one for creating an innovation environment. Step number two is it has to be a physical environment that's conducive to innovation. It's not enough to say, be innovative and go sit in a cubicle. It doesn't work. It's not innovative. Even government furniture is not conducive to innovation. First thing I did is I threw out all the government furniture and we bought designer furniture. And I got a lot of flack from my management for having furniture that looks too nice. And I said, no, it's psychological. When you walk into a room, it sets the tone of how your brain works. Everything in our lab is red, because red is a color of energy. So Stanford D School of Design has studied this. Your environment matters. You react to your environment. So you have to create an environment with also the resources, computers, 3D printers, everything, rapid prototyping. You have to have that to be innovative. So that's what SwampWorks does. The lab that I co-founded, SwampWorks is a group of labs. The lab I'm in is granular mechanics and regolith operations lab. Granular mechanics is, regolith is the crushed rock on the surface of the moon or any planetary body, has no organics in it. That's the main thing about regolith. We study granular mechanics. It's how granular materials behave, the physics, the science, and then the regolith operations means the engineering. It's how do you manipulate it, how do you handle it, how do you do construction with it. The expertise we have is regolith, robotics, and space resources. I'm just going to show this real quick. This is a video of the infrastructure pilot excavator. It's a robot that was invented and developed in the Granular Mechanics and Regolith Operations Lab at the Swamp Works, and it has a mass of 35 kilograms. So it doesn't weigh very much on the moon at all, maybe it's the equivalent of 6 kilograms on the moon. So there's no reaction force. And on Earth, if you want to dig, you have a big yellow machine made out of steel, and you have a lot of reaction force, and you have a big bucket, and it digs. You can't do that on the moon. There's no reaction force, and this only weighs 35 kilograms because our landers are quite small right now. So we reinvented it to have lots of little scoops on a bucket wheel, which is on a bucket drum, and then 2 bucket drums counter-rotate. The reaction forces cancel each other out, and now you can dig on the moon with no reaction force. So that is what this robot will do. And it also will set several records. It will excavate 10,000 kilograms of regolith over 11 days. It will drive about 70 kilometers. The world record for driving on Mars right now is about 45 kilometers, so it will do substantially more driving, and it will drive faster. When you drive on Mars right now, those rovers, they literally drive at the pace of a snail, very, very slow. You send commands up, it drives, then you wait, then you send more commands up. It's a very slow process. This robot will go much faster. One of the main things about SwampWorks is iterative design. We have something called a helical design process. Start small, iterate, and keep getting more and more rigorous until you get to technology readiness level 6, TRL 6, and then it's ready for flight into space. So iteration is a key tenet of SwampWorks. And what our group recently realized is that the Artemis program is trying to put humans on the moon, but that's a big step. That's not a small iteration. And it's really betting a lot of money, resources, everything. You're betting a lot on one mission. And that's really not how successful engineering works. Successful engineering is iterative and incremental with lots of testing and lots of failure along the way, so that by the time you do have the big mission, you're successful. So we've come up with this concept called the Lunar Innovation Park. There's also one other thing I'd like to say is urgency. In Apollo, everybody felt the urgency. We were in a space race, and it was the Cold War, and it was existential. We don't really have that urgency right now, but we're trying to communicate and invoke a sense of urgency about the Artemis program because we are, in fact, in a space race with China. So there's limited real estate on the moon that is good, that is near the resources, and that has enough solar power to survive the shadowed periods. So we do have a sense of urgency. This Lunar Innovation Park is a concept for a rapid lunar proving ground. It's a small iterative step on the way to having a big Artemis program. And I'm just going to click through a little storyboard here that explains it to you. First, you have a CLPS size, so it's about between 100 and 500 kilogram class lander. It lands on the moon. Once you've landed, it deploys a vertical solar array tower. This gives you power. So the first thing you need in space is power. Then you'll see an excavator there, and the excavator is preparing a landing site for the next lander and a berm. The berm protects the first lander from the ejecta from the second lander, because there will be ejecta at 2,000 meters per second that will sandblast the first lander. So it keeps building that berm. Then the second lander comes. The second lander is protected. The first lander is protected from the second lander by that berm. And meanwhile, there's 2 excavators now that have come on these missions, and those 2 excavators keep preparing the site for subsequent landers. So they're building berms and landing pads. So here's the third lander, but it's the first lander that doesn't have a vertical solar array tower on it. In fact, it's a big battery pack. So the solar panels, solar power towers, they recharge the battery pack, which will let you survive the lunar night and the shadowed periods. But then you have to connect that battery pack to the vertical solar array towers. And so you have to excavate a gap and deploy a cable. This is all robotic, no people there. And deploy a cable and connect the power to the batteries. Once you have that, you start working on your next mission. And there's the next lander comes down, and now we excavate a little gap there again, and we deploy the cable. And now we're building we have a system called Armadas, which is a modular structural truss-like system built out of voxels. Voxels are volumetric pixels, and it can be completely robotically assembled. And we're building a lunar garage. And so we have a lunar garage, we cover it with regolith, and now our excavator can go into the lunar garage and shelter there and recharge during the lunar night, and also be protected from micrometeoroids, thermal swings, and just have a safe place to recharge. Now we're pretty much open for business. We have power, we have a battery pack, we have a lunar garage, and now the customers start coming with payloads. So they bring payloads down and they start deploying the payloads out on the, let's see if here we go. These are payloads, this is the excavator, and so these are customers that are visiting, paying customers. And meanwhile, we're preparing new landing sites. So the key to this whole thing is the berms. The berm is a civil engineering structure. It's not a pile of dirt, which I've heard it described as a berm being a pile of dirt. I said, please stop. It's not a pile of dirt. It's a geotechnical, granular material engineered structure. It's a high-tech thing. This berm is going to require a lot of research and modeling to get it right and to make it withstand the blast of the plume. So this berm is an aerospace structure and will be the first off-planet civil engineering structure ever built by humanity. Then the other landers come and we repeat. This is all rinse and repeat, 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 repeat. Finally, we end up with the Lunar Innovation Park. The Lunar Innovation Park is robotic. It's designed to retire risk. So we bring the critical technologies to the Lunar Innovation Park to accelerate the Artemis program, because now we can take more risk than we would on a human mission. By the time the human mission happens, we've retired the risk and we understand the lunar environment, and then the whole program ultimately is more successful. This is a bird's eye view, overhead view, and you can see that here's the Lunar Innovation Park, and now we start building the permanent landing pad. This is the first step to a lunar spaceport. The entry and exit point of the South Pole will be lunar spaceports. And lunar spaceports will require landing pads with safe conditions. And what we're not showing here is all the services. There will be propellant loading services. There will be cargo offloading services. There will be all kinds of services that happen around this spaceport. But more importantly, it's a hub of economic activity. So if you want to be successful on the moon, it has to be economically viable. On Earth, seaports, airports, they all make a lot of money. Spaceport will be the first money-generating endeavor on the moon, and this is a precursor to the spaceport. I hope I didn't go over too much.
Perfect. I'll let you go up.
Any questions now?
No,
Okay.
we'll wait.
Deal.
Okay, just hang in there, and then Okay. We talked about, Rob talked about the spaceport. So this next talk will introduce Luniverse and Lunar Spaceport 1 as a case study in the future of infrastructure beyond Earth. Designing a lunar spaceport is a challenge involving terrain, plume effects, power, communications, logistics, robotics, traffic management, and surface construction. On Earth, infrastructure can be tested, repaired, and adapted through physical iteration. But the conditions of the moon cannot be fully replicated in a unified terrestrial testbed. So it must be coordinated digitally before we get there. Luniverse is a simulation environment that includes all of those elements. But it's also a simulation for lunar and space economy, as Rob said, which includes governance, finance, insurance, and long-term economic development. Mouse McCoy, officially Michael McCoy, but we all know him as Mouse, is founder and creative director of Studio 52 and the co-creator and director of Luniverse, which was inspired by his previous work on the Luna 10 DARPA project. Studio 52 provides digital studio infrastructure using AI, spatial computing, simulation, digital twins, and operational 3D worlds, all designed to make complex realities visible, understandable, coordinated, and actionable. Before Studio 52, he founded Hackrod to explore AI-enabled design and generative engineering for the manufacturing and distributed production of cars. Prior to that, Mouse co-founded Cantina Creative to help Hollywood design futuristic interfaces, synthetic environments, and spatial operating systems for major films including Iron Man, Avengers, and Avatar. He also produced and directed Act of Valor, a #1 box office film created with naval special warfare, and produced Dust to Glory, a motorsports documentary about the Baja 1000, while actually becoming the first Baja 1000 Ironman motorcycle champion. Really, now you're just showing off. Yeah. Welcome, Mouse McCoy.
We're not ready to do that yet.
Okay, you don't want to do it.
All right. Good afternoon, everybody. Let's have some fun now. I think I saw everybody starting to have fun here, and that's cool. I'll tell a little bit of story how they got started. So as you know, I came out of entertainment, and we were designing the future for Hollywood. And then I said, when is this going to be for real? When is that intersection of entertainment design and engineering and simulation going to come together? Because this was going to be the moment of interface that everything was going to change. So I'm going to get to that. But here's how this journey got started. We had been doing quite a bit of complex simulation and world building for the Department of Defense and various commands. And DARPA came along, and DARPA wanted to figure out how could they help the cislunar and lunar mission, and how could they look at the emerging space economy. So there was a meeting that was held at our studio, and we have a kind of a known innovation program called campfiring, where we sit around the campfire at night and have blue sky ideas and then hit the whiteboards in the morning and take crazy ideas and make things. I like Alex. So we get together, 12 of the top private space companies in the world. Can you guys hear me good enough? Yeah. So 12 top private space companies, Phil Root, the director of the STO at DARPA's Strategic Technology Office, got together and said, how can we help? What can DARPA do? And Rob was there. Everyone just got quiet. Nobody would talk to each other. I said, Houston, we have a problem. This is going to be commercial space, is going to be an interaction or a system of hundreds of companies. Right now, nobody will talk to them. Everybody's in their IP box. Well, I'm not showing you my plan, not telling you. Well, you guys all have to interface. You all have to work together. It's not a discrete mission anymore. So we had an idea, well, let's figure out the emerging lunar economy, but I said, how are we going to build the architectural framework to allow the coordination to happen? Because it became really understandable that we had a coordination problem, not a technology problem. So this was the thing. So I'm going to show a couple films, but these aren't really films to look at like films. They're communications. But the first one will be, you'll see, this is not Hollywood CGI. This is a full geo-rectified 3D model of the moon based on lunar reconnaissance orbiter data. So it is a geo-rectified model, the whole moon, and it's in a simulation. All of the orbital mechanics are fully accurate, sun, moon positioning, everything. The gravity's installed in the simulation. Everything is put in here. So this is the beginning of a digital twin of the moon. You can call it lunar virtual twin. We are connecting the data sets right now. But I'm going to play these first. and then we'll talk some more. The DoD set out to study the first 10 years of the emerging lunar economy. To help achieve this complex simulation, we needed to build an immersive digital twin of the moon and an industrial metaverse framework that allowed simulation of multiple digital twins in a system of systems and create a common operational picture of the emerging lunar requirements for capability development. We need to focus on communications, power, in situ resource utilization, to harvest the resources on the moon, to help create a sustainable footprint moving forward. Transportation. This industrial metaverse simulation is the foundational framework of a hyper-accelerated digital twin future for cislunar development, and the first vision of the requirements for Spaceport One. Play the companion film that seems out of sequence, but it's important to support the premise that we are talking about the interoperability and interfaces between everybody. Without that, the mission doesn't work. Oh, we're not seeing it. We're at the dawn of commercial space. What was previously the domain of large government agencies. Yeah, but it's not on the screens. There we go. Of artificial intelligence, the industrial metaverse is now enabling startup private space to compete on an exponentially lower budget and exponentially greater schedule. Commercial space is going to be primarily a robotic mission. And currently, all of the digital twins of these robots have never interacted. They've never been in a simulation.
Mouse, are you narrating that, or is that a
Yes.
computerized version of your?
No. But you can do that now.
Yeah, I was just wondering whether it was.
Robotic mission will build the infrastructure and pave the way for future. Okay. Yep. We're at the dawn of commercial space. What was previously the domain of large government agencies with big budgets has been democratized by digital technologies. The rise of artificial intelligence, the industrial metaverse, is now enabling startups, private space to compete on an exponentially lower budget and exponentially greater schedule. Commercial space is going to be primarily a robotic mission. And currently, all of the digital twins of these robots have never interacted. They've never been in a simulation together. They don't know how to work together. We now have the ability to, through the industrial metaverse framework, interconnect this system of systems and build a real-world physics-based engineering simulation of the robotic mission. The robotic missions will build the infrastructure and pave the way for future human missions. The emergence of, or the training of, robotics in a synthetic space is upon us. The AI agents that will be controlling the robots should be interacting through an AI-powered industrial metaverse to perfect the mission profile before they ever deploy. Once again, that's not prop sending, that's all CAD of all commercial space companies and the equipment. That's basically the loadout. That's what it looks like physically, not in the Excel spreadsheet. So let me back up because there's a very couple points of interface here that I want to bring up. So I said this convergence of engineering, entertainment, visualization, and data. So how many people in the room have heard of OpenUSD, Universal Scene Description? 1, 2. Okay, write this down, everybody. I wanted to encourage it, and the OpenUSD Alliance. Standards matter. Standards drive everything. So OpenUSD was created by Industrial Light and Magic and Pixar to create movies. It was the universal scene description for 3D objects and 3D worlds. They open sourced it because they needed every company in Hollywood that was startups and small visual effects companies to do shots on the movie. So USD solved all our problem. We're working in complex 3D environments. That's how we think. We see the world in 3D. Well, engineering had a huge problem. There was no compatibility of file formats at all. So NVIDIA, Siemens, Adobe, Autodesk, who you all know real well from AEC, and I could go down the list, they formed the OpenUSD Alliance to standardize all of this. So all of your 3D interactions and worlds are now unified. This is also the operating language of robots. So robots are going to train in synthetic environments. They're going to do machine learning. And as we said, this is the foundation for persistent world models and data to flow through. So this was like, boom, wow, everything changed. So from that moment, also another standard with systems modeling language, SysMLv2 came along. So now you can take all of your systems engineering, your requirements, and all of your data, power attributes, everything, and it's machine readable now. So that standard format, connecting into USD, now we're building a holistic world that is alive and intelligent and interoperate. So now we have interoperability or a common operational simulation. Without this, the whole commercial space mission just does not work. It's not a discrete siloed mission anymore. Fundamental. The other parts is the technologies emerge simultaneously but in parallel. This is the moment of interface right now. Okay, we all know robotics, AI, big, massive cloud compute, simulation, everything's converging, and now it can be converged into an operational environment that hadn't been conceived before. Now we can also start to interface. Why this isn't a platform or a simulation, by the way. I'm not selling anything here. It's run by a non-for-profit, and we're building national infrastructure. So this will be national space infrastructure. The standards have been aligned. There's working groups right now. So I'm gonna keep this short in the Q&A. So what happened is we spun this out of DARPA. DARPA Luna 10 became the Luniverse. It was vetted for the last 2 years by a coalition, a conference like this, but grew to 1,000 people. NASA, JPL, Aerospace Corp, Johns Hopkins, and all private space came together, and we've ratified the standards, the architectures, and the interfaces. We can all work together now. Like, for us, this is a really big moment, but this is going to be consistent throughout all of AEC, construction, and civil engineering. Systems engineering design is going to come together. I'm trying to paint this. And there's a question earlier about, well, how do we know fidelity in the simulation and the data when your designers are just working over here? That's now merged. So now the design can be simulated almost in real time as it's being built. So then we have standards, we have foundations, now we can intercommunicate. And then you start to ingest the models, the assumptions, the cost, and now the foundation of the solar system or the space economy grows out of the requirements and the needs and the cost. So then we're going to get back to system of systems, right? Well, now let's just look at acquisition and procurement of anything. So some startup comes along and says, hey, I got this great little thing, you know, and it's going to be worth a lot of money. Well, where does it fit into the system? How is it even in the simulator? If you're a VC, how does it work? You're going to be able to see this and work it and prove out your engineering design before it's even created. So this is the moment of interface. And this moment of interface is going to happen across industry direct overall. So it's a lot of fun, it's inspiring, and it's also democratizing. You know, you're not going to have to be Lockheed Martin and the bigs. They don't control the domain. You're going to see private space, commercials, and startups flourishing inside of an environment like this. So that's what we're working on. I'd rather have some Q&A and questions and kind of break this up a little bit. But I'd want to say thanks to Alex and Craig earlier for saying, why are we listening to this movie, dude? And what we're trying to do is like what Imagineering was. This is Imagineering now. And so for the next generation, the students in here, think differently. Think Imagineering, because your imagination is going to be brought to life in a way that was never possible before. So I hope I didn't go too long.
Thank you. Thank you, Mouse. Two things. One, next time you hold a campfire session in Ventura, I need to be there. And two, a message to you talked about the consortium of companies and all, but this is the moment for all of you at universities to get linked in with this, with this issue. And if you could just talk about that.
Yeah, I do. And I forgot one point. It's a little bit in the weeds. But all the models you saw in there, we started working exponentially faster. The design team, like this is a big, interesting point. The design team, which was working in the 3D model of the digital twin of the moon, we started creating requirements, just started falling off the page. Because people weren't writing requirements on a spreadsheet in an office somewhere, is we were experientially generating what the needs are overall for the mission. So super important point, that train you saw, that was Northrop Grumman's railroad. They had designed a railroad for the moon. They had no idea how to interface it in. In about 2 days, we did the slope analysis, all the terrain study, and we routed it on a 30-kilometer route and then built it. They wanted to do comms relay networks. Firefly and Blue Origin were crashing MATLAB like crazy. They couldn't figure it out. We went, ooh, hey, here's the 3D model of the tower. Boom, put it right there. Shoot the laser. There's the rally point. There's the rally point. We architected a comm relay network in 3 hours, not a team of PhDs over 9 months. This was how fast you can start working in these 3D worlds. So we're going to see an exponential acceleration. That's what I wanted to make sure I led, is just this is an exponential moment we're all rolling into. Sorry, Jerry, I didn't.
Perfect.
Okay, so
Thank
there's
you.
a question.
And university involvement.
Yep. All right, so really quick, this is so cool for me to be at a university because it's really at the heart of us rolling this out. So how many people are familiar with the history of ARPANET and the internet? Yeah? Oh, okay, that's pretty good. So ARPA was DARPA's switch packet network. So they were the Advanced Research Project Agency, so they built their first network. So this was the first switch packet network. Well, then the universities came in, and they started to hop on the nodes. Each university was building a node, and a network was formed. The standards were agreed upon, right? We all know that the architecture of the internet, and the internet was born by universities and standards bodies. So this is spinning out, and we're going to build it with the universities. So right now, Purdue and Georgia Tech, who are two of the leading aerospace design schools, they're running point for the rollout, but we envision a multitude of universities, because the problem of Lunar Spaceport 1 is really, really hard and big, and it's going to be multi-interdisciplinary. So we're creating the grand collaboration. So I didn't want to talk earlier to my team about grand challenges, but the grand collaboration is the framework that will allow everybody to collaborate in one large 3D simulation. And then they can interface with commercial. But we start with the university so we can test it. We can build it, and we're going to proxy build Lunar Spaceport 1. But the requirements are going to come because nobody else is really writing them. NASA's trying to write them. I don't want to talk for you guys. But anyway, so this is really exciting, and we'd love to talk to anybody with universities, just get to know y'all. So
We'll go right to the next one, and we're going to save Q&A till after Dave comes, so we'll tee up Dave's now. As soon as I find my intro. In support of these NASA efforts, the IEEE Telepresence Initiative helps develop new solutions in human-machine systems, robotics, and cybernetics. Telepresence technologies enable a user's remote presence at a different physical location. Telepresence has wide-reaching applications in space and undersea exploration, search and rescue, healthcare, education, manufacturing, and entertainment. IEEE uses telepresence, one of their many initiatives, to help NASA create events as well and educational activities. A notable one was the second annual Robopalooza Space Festival last year in Perth, Australia, supporting advancement of automation, robotics, remote operations, and zero emissions technologies. Dave Magnoni, thanks for being here.
Thank you for the introduction. So yeah, I'll just talk briefly about IEEE. We're a fairly large professional organization focused on advancing technology for the benefit of humanity. And we have a lot of members, we do a lot of conferences, we publish a lot of things, we produce standards. So there's a number of different things we do. One of the activities inside of IEEE is a group called Future Directions. That's the group that I'm in. Future Directions, our charter is to identify and help to grow new and emerging technologies. We do this by working with our volunteers and the existing units at IEEE to build a community, get things going, create new conferences, things like that. One of the things that the team does is we help focus on collaboration across the OUs, which usually isn't as challenging as getting developers and environmentalists to talk to each other and focus on solutions, but still, it's an important function. And so that's one of the things that we're there to do, is to help enable volunteers to innovate, to create new things, especially in the focus areas. There's a number of different things we do. One of the biggest things in the upper left-hand corner, I know it's an eye chart, it talks about the different initiatives. So there have been initiatives over the years, IoT, quantum, smart cities, you name it, a group of volunteers has gotten together and created things, and a lot of times these things persist. They either go into the societies and become a new focus area inside an existing society, or they form new organizational units inside of IEEE. There's also a group, a fairly large group, that focuses on what's going on in the technology world. What are the trends that are driving different technical changes? And the Industry Advisory Board produces a report talking about, here are some of the big things that we think have potential to impact humanity, and here are ones that are potentially high impact but a little bit further off, whatever. There's other things like roadmaps. So roadmaps are actually interesting because they represent a 5-10-year vision of the problems we need to solve to make semiconductor manufacturing better, to make non-terrestrial communications better, things like that. So there's actually quite a bit of stuff going on in the group. But as we mentioned, sorry, I didn't realize this was a build slide. This is what we're working on right now. These are the active initiatives. More initiatives are being defined. In fact, one of the things I'm working on is not on here. It's a focus on space technology that we will be defining later on this year. But the one I wanted to focus on now was the telepresence. This was done by a group of volunteers that identified telepresence as a key enabling technology to allow you to work from anywhere to anywhere. And it's increasingly something that has to be considered in space, right? Even if you're close enough to do something, would you really like to step outside and fix it? Or would you like to make sure that the robot can take care of that for you, things like that. One of the things we do is we help the team do the activities, create events and do workshops and things like that. And sometimes we get a chance to do some fun things. Like the next thing I want to show, and I'd like to ask Rob to come up and talk about this, because one of the things the founding members wanted in the telepresence initiative was to do a competition, right? Something that simulated running a rover around remotely in space or on the moon. And so we found a volunteer to do that, and Rob answered the mail.
You've heard of the term voluntold, right? Since we're storytelling here, I have a very quick story to tell about this. I've been running a competition called the NASA Lunobotics competition, which is excavation robots on a simulated lunar surface for universities. Since 2010, we have over 50 universities that come every year, and they learn systems engineering, and they build a robot, and then they graduate. So it's a really good training program for students for industry. They graduate, they're systems engineers, and they know robotics, and they've actually built something. So we have a lot of sponsors that just love to hire these students. But Dave and a few others came to me and said, hey, you know how to run a competition, right? I said, I think so. And they said, well, why don't you run this telepresence competition? I said, what is it? And I said, well, anybody in the world can drive a robot at another location, and we'll have a race, a robot race. But the people driving it are not where the robot is. So they could be anywhere in the world, and we did. We had people in every continent doing this. So they asked me to do this, and they were at Caltech that year for the conference. So the Mojave Desert's about an hour and a half drive away from Caltech. So we did it in the Mojave Desert, and we had this competition, but there was a problem. It was not very spectator friendly. There was a robot in a field driving around, and all the drivers were somewhere else in the world. And it's like, this is a really tough one to promote. How am I going to get people to get excited about this? And so that's where the innovation comes in. So we said, well, the competition is going to happen. IEEE is going to be happy. That's fine. But the public is not going to be happy, because all they'll see is a robot with nobody driving. It's going to be really boring. And so we said, okay, we have to be innovative. Let's wrap a festival around the competition. Food trucks, music, demos, dancing robot dogs, and all that stuff. And so that's what we had to do to get everybody excited, and that's what we did. And we had 7 teams in the first year. The tent, this was all logistics, was really hard. We had a tent set up, and the night before, a 40-mile-per-hour wind came and blew the tent away, so okay. That was a challenge, but that's the way it is on the frontier. And then a team from Australia won. And then they got so excited that they said, well, why don't you come to Perth and run it in Perth? So we did, and so we had the second Robopalooza in Perth with 9 teams, and we ran and we had a kind of a trade show thing with a lot of robot demonstrations. We even had a guitar, a robotic guitar, playing music robotically. So it was really innovative, and the mining industry is behind this, because now, it used to be they used to fly people into the outback to the mines, 3,000 kilometers, and then they'd go fly out on Monday, come back Friday, they miss their families. They don't do that anymore. They sit in an office in Perth, and they tele-operate all the equipment in the mines, and they can all stay at home, and it's much cheaper, and everybody's happier. So this is a very good use case for telepresence, is remote mining. And we saw that, and the Australians understand that, and it makes a lot of money. So they invited us down there to a proving ground that they have built. So that's all great, very successful. But now what? Well, we're into the 3rd year of Robopalooza, and we've proven the concept. We scaled it up in Australia, and now we're ready for prime time. So this is the 3rd year, and now it's like go big or go home, So where are we going to do this? Well, we have to do it in the Bay Area, San Francisco Bay Area. That's where all the capital is. That's where all the robotics companies are. That's where the interest is. So there's going to be a conference called Robo Business the week after this Robopalooza. On the 17th of October, we'll have this Robopalooza. And it's actually, that's the Gitai robot. That's a solar power tower self-assembling itself. So these are real robots. This is not science fiction. And we're going to invite everybody there to have this big robot party. And we're going to have space-themed robots. We're going to do embodied AI, physical AI, because that's what's happening right now. And we're going to have live music. We're going to have a major act there, maybe several, and have a music festival. So this is what it takes. This is what it takes to excite people. I'm sorry, but sitting in a conference room doesn't excite people, especially if you're under the age of 30. You know, that's not exciting. We want a nightclub line out the door trying to get into this event. And that's what we have at Robopalooza. People lined up to get in. Why are they lining up to get in? Because it's exciting. So we're making this really exciting event. We're taking it up one notch now. Dave keeps pushing me, take it up a notch. So now this year we're having heterogeneous collaborating robots racing to mine water ice from a lunar lava tube. We're going to have 3 robots, a wheeled robot platform, a ground control robotic snake robot developed at Georgia Tech University and now commercialized, and then a drone for an eye in the sky. And those 3 robots all have to collaborate to find the water ice in the lava tube. Fastest team to find the water ice wins. So it's a race, and it's a coordination problem of doing 3 robots together. We'll have a prize money, and it will be super exciting. But why are we doing this? We're doing it because we need people. We need the skills. We need, all these different skills, robotic engineers, AI developers. We need these skills. And that's what's in it for the companies that sponsor this event. They get to hire these skills. We'll have speed dating tables set up, and you go speed dating for a job. Thank you.
Thank you, Dave. Thank you, Rob. Let's have all 3 come back up, and we'll take just a few minutes for a couple questions. The first one popped right there. Yep, you got it. And then over here will be next.
So, Robert, question for you. SwampWorks, or generally known as SkunkWorks, or formerly known as organizational ambidexterity, is something that you only find in 2 places. One is the federal government, in a handful of agencies. NASA is one, ARPA has been another. The other is private enterprise. You do not find SkunkWorks teams in civil infrastructure governing agencies below the federal level. I'm wondering, and I think there's a reason for that. I think it's because, generally speaking, you could flood all of New Orleans, and the stormwater agency is going to be there afterwards in a slightly different form with different leadership, but there's no competition, right? So I'm wondering if you've learned in your work on the SwampWorks lessons that we might take to civil engineering organizations to deploy that framework and open up innovation there.
Well, I think the desire is there. Turner Construction asked me to come to their innovation event. They have an innovation conference every year, internal, just for Turner Construction Company employees. They rent it out at, what's the football stadium in New Orleans called? The Superdome or something? Superdome. They rented it out for this event, so it's a big event, not the whole dome, but they had the conference area. And they asked me to speak about innovation in construction. I spoke about 3D printing with concrete and that kind of thing. And they were interested in it. There's not a lack of desire from the AEC industry to do skunkworks type of development. It's the legal structure that's out there. It's the liability. Nobody can take the risk because of the way our tort laws are structured for liability. So you know better than I do when you're in construction, you can't afford to mess up because you're going to get sued. And if you get sued, your company's gone. So what are you going to do? You're not going to take a risk, which means you don't innovate. So we need kind of a proving ground, construction proving ground, for where you can take all the risks without having liability. But you can't go into construction until you're at TRL 9, which is operational. So I think that's my answer, is liability.
And thank God we're not going to do tort reform for the whole government, right?
I wish we would.
I know. Go ahead.
Yeah, this is for Mouse. For education, it's sort of a 3-part but huge question. When you look at the undergraduate curriculum, what do we need to teach? How do we need to teach it? And who's qualified to teach it?
So we had this conversation already at our desk. We already answered this question over lunch. So different people have different opinions about AI. I know a guy in my lab who wanted to have a fist fight with me about it because he says it's ruining us, you know. But it's what you make of it. Personally, I'll let everybody else speak too, but I have one quick one-line answer. When I was in college, university, they told me, here's the question and the answer is in the back of the book. That model is flipped. Now the answer is everywhere. What's the question? So we need to teach students what is the question, and at lunchtime we're discussing what is the process you follow to arrive at the answer is more important than what is the answer, because the answer is probably already out there.
When you see the persistent 3D worlds, that's all the engineering interfaces. That extracts visual storytelling that can be made into curriculum. So the first phase is we're looking at education significantly as an output of this. Just like I can make a cool guy movie, but it's really the engineering. But now let's make exciting, engaging, experiential education to start to teach differently. That's a conversation. I'm not an educator, but I know how people that grow up in Hollywood in the film business that don't go to school, they do it. So I think the education, but now to play on what Rob said, what are you building yourself? I feel like if you're a student, now you have all the tools you need to develop something. You can develop your own digital robot. You can develop digitally whatever you want. And to really kind of somewhat quote Elon, is show me what you've built. So I think the encouragement should be a lot with a problem definition, but then the students, they have to solve the problem and then create the answer by that. That's, I think, the best way I can succinctly hit that.
And I would, if you don't mind, Rob, you know, when we did Future World Vision, and Jane is back here somewhere, last I checked 2 years ago, I think there was well over 100 universities were using that platform in some form or fashion. Real curriculum to special project. Luniverse and the concepts that Mouse talked about, I mean, I think are the next giant step for actual using the actual device, the environment, is part of your educational curriculum. I think that's what's coming.
So let me hit on that, because this is a really big point. And I used to get thrown out of conferences and accused of being a heretic, and it was bad, right? It's like, this movie dude told me to get out of here, because I said, well, engineering is going to be gamified. And so it's now a 3D environment. So the natural language of the next generation coming up is that gaming interface. And we sort of joke that this is like Minecraft for PhD students right now. But you grow up playing Minecraft, building worlds all the time, you're naturally going to, and then you can start to build interoperable things like a game. So now your engineering project is the same structure as if you're building a module for Call of Duty or Fortnite, whatever. So this is a really big thing, and this is unavoidable. The engineers hated it, but it's like, thank you for all your knowledge, guidance, and everything. Things are changing. I'm sorry, I have to say it, like right now I can see people with no experience make a movie on AI that looks pretty cool. Okay, well, you're going to have a different pipeline, and the barriers to what the young innovators and the motivated can do, or they've never existed before.
Next question, who's got the mic? Back here.
So at least one of you mentioned issues with interoperability and the need for standards. And once standards were developed, then all systems go. So are there other standards that are missing that you see in the future? And is there, because you've been involved in this, processes that can be used to better create the standards that we find that we're missing as we move into the future?
Yeah, I want to hit that a little abstractly if I can. Standards are obviously going to set the architecture, but the interactions of the digital twins, and I think we all have to really talk more about the significance of digital twins. So, and those digital twins will become intelligent on their own. So then their interactions in the future, we've set the core architectures, but the interactions are going to drive new standards. and the system itself will start to improve itself. And this world starts, and these persistent worlds start to self-accelerate and update. So it's data, models, simulation, evidence, repeat. So
Okay.
I hope that answered it.
Next one.
So I think this question is for you, Rob. I was wondering whether you can go a little bit further than the high-tech pile of dirt that you mentioned and share thoughts that your group has developed on in situ material utilization that goes even beyond regolith cindering. What are the key ideas that will allow us to use materials on the surface of the moon?
Yeah, so
And elsewhere.
we have something called in situ resource utilization, ISRU. It's a whole field of knowledge, and we have conferences dedicated just to that subject and groups working on it, and even PhDs being done just on this subject. So what is a resource is the first question we have to ask. What resources are there, and what can we use? So the first resource is energy, sunlight, and we already use that today in orbit. So that's well understood, well used. So we can already say we're doing ISRU. Some people say, no, that doesn't count. I think it counts, but some people say, no, you have to be using regolith materials. So I say, okay, let's use regolith. So what can we do with regolith? Well, easiest thing to do is bulk regolith. Bulk regolith has a particle size distribution from about submicron to, it goes up, of course, to millimeters and meters, but bulk of it is between 20 microns and 100 microns. So now you can do, if you're a granular mechanics person or a civil engineer, you understand that particle size matters. So you can use different particle sizes and sieve that regolith out into different particle size grades and then use those for different applications. Like for sintering, some is good, and for gravel roads, another size is good. So right there, you already have a product. That's a resource, a regolith resource. So regolith by itself, bulk regolith is a resource for civil engineering purposes. But then if you want to go further, then you have to extract the metals. So most of the resources on the moon are silicates. It means most of the moon, the minerals are 42% oxygen, and the rest is some kind of metal or other mineral. We have aluminum, iron, titanium, various other metals, but those are the magnesium is the other one. They are there. If we extract the oxygen, we can use it for breathing air and propulsion for chemical rocket engines. So that's the next obvious step, is to start extracting the oxygen, and the byproduct is metals. And then we can start 3D printing with the metals. But you can also melt the regolith into glass fiber and then weave it into a textile, and now you have a composite material, and you can use bioresins by growing plants and then converting that into resins. So this whole economy starts developing from in situ materials. Now we can go on and on, but you get the idea. And I'd be happy to talk to you offline, but there's a lot more you can do.
Okay, we only have 2 more questions. Mark's got one of them.
So, Mouse, this is for you. Oh, there we go. The simulation in the virtual twin is fabulous, and I can see how you build things. But the entire IAC community has a million different virtual twins. How do we get them involved in in connecting their virtual twins so that they can use their tools and their infrastructure on the moon? And one thought was, can you make a virtual Earth so all the same technologies cross over them?
Yes, NVIDIA has been playing around with digital twin of the Earth. Overall, the term, well, I want to say the term got burned into the ground for a while. We wouldn't even use it. Metaverse, it was like that silly cartoon thing that Zuckerberg built. But Siemens, NVIDIA, Autodesk, they're all talking about the industrial metaverse. Siemens' one big new product is Digital Twin Composer. Same thing, it's a subset. Our architecture, back to the standard interface, allows all of the solvers. So those standards, like Siemens' main file format of JT, goes to OpenUSD. That's how it goes into NVIDIA, and it works in Omniverse, trains the robotics. So the concept of industrial metaverse is how you're pre-building factories, everything on Earth. You're going to, in my opinion, see an explosion of this now, because we finally have the compute, we have the cloud, and AEC will be able to now interface, and I very much would see, and somebody should go ahead and do it. We got our hands full with the moon, but to start to build large metaverse instances that can connect entire projects. So when Imagineering was talking before, he was alluding to, they worked their way into this. They were basically, and Alex is doing that over there. This is not pre-visualization anymore, this is world building. And so now if everybody, Craig's chart with that little Star Wars with the Death Star thing and all the people around it, they should now all have interfaced into one dynamic. But this is, you're seeing it visual. Like change update comes through. Okay, boom, let's go back in today and connected engineering now, not silly cartoon land. It's validated back to the twin. So let's go and look at the new proposed site development here. And you all see it in real time, just like going to the job site. So I think this will be a pervasive movement across the board. There's really no other way. It's not just my opinion. I'm quoting like NVIDIA and all these other people. So
This is the way.
And last question, unfortunately. Ava, you have the mic.
Yeah, you're all talking about world building, which is fantastic. With regard to artificial intelligence, which I actually, every time I hear AI, I interpret it as automated inference, because there's nothing artificial or intelligent about computers. So in the automated inference world, you're now building world models. You're calling it world models. Large language models are so yesterday. The next chapter is world models. So I'm wondering whether any of you are working with Li Feifei at Stanford University or Jan LeQuinn at NYU at AMI, because they're actually building the synthesizing reasoning models that need your data to be able to come out with world models. It seems like unless you're working together, you're on parallel tracks.
Part of once again, the university is coming in. We really want grad students to also to go to work on this. We will have be a content use case. So with like Jan LeCun or the other people building persistent world models, this is the frontier from AI. You said it very well, and I do agree. It's a mimic, not a mind. Like that always throws me right now. So
Automated inference, that's what it is.
that's correct, 100%. When you have, then the digital twin starts to become the interaction point that will build the persistent world. So I look at it as we're developing for that. Right now, we're doing great work, and it's like we're doing everything, but we're basically anticipating that moment, that breakthrough, and then you can imagine how this goes from there. Yeah. So this is not a foundational LLM construct right now.
Yeah, let me add one thing to your world modeling is the data that we need. NASA has it. It's called PDS, Planetary Data System. And we already have it open sourced, and the whole moon has been mapped with the laser altimeter. And so we have the topography of the moon. It's getting better all the time with new instruments going up. So that 3D world that you're looking for instead of the LLM, we have that. But it's on the moon. So, somebody talked about the digital Earth. Digital Earth is great, but it's too complicated. Moon, it's too much people, too many legacy systems in the world. So you can't break into the Earth because there's too many legacy social structures. Moon is a blank canvas. So the moon is the perfect place to start doing world building, not the Earth. The Earth is has too many legacy systems associated with it.
And the last bit, because I want to just back, so that spatial data, so it's NASA's spatial memory of the moon. That data was only accessible by exquisite mission teams before, like JPL could know what to do with the data. With System LV2 and the ability to now interface that data into OpenUSD and connect it to the systems modeling language and the model-based systems engineering, now this no longer, see what I'm saying? So that was a really big first use case. And we might end up working with somebody like that to actually really keep going. But this is what we're doing. Great question.
Okay, I need to apologize to Dave, first of all. You know, I don't know how you keep up with or put up with these two guys, but I want a round of applause for all three of them. And with that, we're on to our next.
Well, actually, what we're going to do is let's take a half break. So half break as opposed to 15 minutes. So 7 or 8 minutes just to run out in the hall, down the hall if you wish, refill a coffee cup or whatever, reconvene here. That'll put